Alright, so we are going to be learning about equilibrium. Equilibrium is when a chemical reaction can occur in the forward and backward motion. So reactants can become products, and products can become reactants. In a chemical equilibrium, the forward reaction is happening at the same rate as the reverse direction. So that means that the rate at which reactants are becoming products and products are becoming reactants is exactly the same. It is a dynamic equilibrium because it is still changing. It is not staying the same. If we look at these graphs, this is concentration over time. At the beginning of a reaction, we have only reactants. There are 0 products. But as reactants are used up and made into products, we see the concentration of products increasing. Well, at some point, the line in this graph has become flat, which means there is no change. The rate of change is staying the same. So the concentrations of products and reactants are staying the same in general, so it has reached equilibrium. This is another example of an equilibrium graph. In this case, the concentration of products always stays less than the concentration of reactants. So we use what's called K, the equilibrium constant, to describe this. It's a ratio. So if K is more than 1, like our first graph, the amount of products at equilibrium is more than the amount of reactants. But if K is less than 1, then the amount of reactants at equilibrium is more than the amount of products, our second graph over here. If they're equal, then K is equal to 1, but that doesn't happen very often. So here's how we get our equilibrium expression. K is equal to the concentration of the product over the concentration of the reactant. And each concentration is taken to the power of whatever number their coefficient is. So that is where you get those exponents, the coefficients. Remember that concentration, we talk about molarity, so that's moles over liters. And the exponents, again, are the coefficients. So let's take a look at how to write an equilibrium expression. Alright, so one thing you have to know is that solid and liquid are, do not contribute to the equilibrium expression because they do not have a concentration that is changing that affects the equilibrium, so we will cross those out. So we cross out our solids, and what's left is our aqueous and gas species. So we're going to write our equilibrium expression. Remember, it's products over reactants. So our product is H2, and it's the concentration. That's these little lines right here. That means concentration. And CO3, 2 minus. And then make sure that we write our exponents. Well, the coefficient for H2 is 1. You can write 1. You don't have to include that. But the coefficient for carbonate is 3. So we must include that in our expression. And so that is what K equals. So let's go on and solve for K. If you are given the reaction, you can figure out the equilibrium expression. And then if you are given information about molarity, then you can solve for your K. So let's first write our equilibrium expression. They're all gases, so we're going to include them. Remember that it is products over reactants. So PCl3, and then if there are 2, we multiply them times Cl2 divided by Cl5. All right, remember these brackets means concentration, which is molarity, moles over liters. And so we are given moles and we're given liters, so you're going to have to calculate your molarity for each one. But that's just a simple division problem. So for PCl3, our mole is 0.32. Our liters is 12, so if you plug that into your calculator, you get this for the molarity. If you notice, the moles for chlorine gas is the same thing, so this is the molarity of both of them. Less math. And then our reactant, we have 0.21 over 12. Now notice that these are the concentrations at equilibrium. That's important. We'll get to that later in this unit. Alright, so I'll plug that in. 0.018 molarity. Okay, so I have all three molarities. I have my K expression set up, so I just plug in and solve for K. So K is equal to the molarity of the two products multiplied, because they are both have a coefficient of 1, it's to the power of 1, so it's the same thing. And then divided by our concentration of our reactant. And when we plug that in, we get a K of 0.041. And K has no units because we are dividing by a bunch of molarities. Alright, that's it.